So our next example is going to be called a biased random walk on an n cycle, and I think you can easily see why it's called an n cycle, right? So there are n states arranged in this circular or cyclical form. So let's talk a little bit why I call it a biased random walk. So if you look at the way you transition here, so I didn't actually write down the one-step transition probabilities. They're just illustrated in the actual diagram. So at every single state, right, you're gonna flip a coin, and if it lands heads, you'll move up a number, and if it lands tails, you'll move down a number, with the exception of the state n, right? So this completes the cycle that when the coin lands on heads, you actually are going to transition back down to state 1, right? So you can write this as a mod function, but let's not go there, right? The picture kind of describes what's happening, and the probability of getting a heads is going to be p, right? So this is a biased coin flip, right? Therefore, biased random walk. In the random walk, it just has to do with the fact that you either move one, kind of left or right, or up or down, depending on how you want to look at it, in a biased fashion, right? So when p is not equal to 1/2, the coin is going to be biased, and therefore biased random walk. When p is equal to 1/2, you could say it's an unbiased random walk on an n cycle. So we can start thinking about whether this is a reversible process, whether it's not reversible as a Markov chain, I mean. And so, I think there's going to be a lot of intuition that kind of saves us here. So, obviously to show anything mathematically, we would have to, try to either establish local balance equations, or we'd have to compute maybe the stationary distribution, or guess it somehow, and then try to maybe compute the time reverse chain and see if its transition probabilities match the original transition probability. So there's all these kind of ways to proceed, but at the same time here, the example is a little bit transparent, right? So your intuition, which you should always try to use first before doing any math, kind of tells you, like, when you think about this being played in a movie, right? And we can even take an extreme case where p is equal to 1, right? When p is equal to 1, you'll see that this Markov chain is just going to be counting from 1 to n, then jump back down to 1, count all the way up to n, jump back down to 1. And so if p is fixed at 1, then you know exactly whether the movie is being played forwards or backwards. It's being played forward when the count is moving in an incremental manner from 1 to n, and then jumping down to 1, and time is moving backwards if we're going down from n to 1 and then jumping back up to n, right? So for p equals 1, it's a pretty clear case that, at least our best guess, and likely going to be a good guess, that this is not a reversible process. For same thing would happen, right? Same logic would apply for q equals 1, and it's a likely, right? Q equals 1 is a likely candidate for a time reverse chain for the one that I just described when p was equal to 1. Right, it seems like all you're doing is you're flipping the arrows, and the probability is still 1 on each number. So one question is, could this ever be a reversible process? And that could very well be, right? When p is equal to 1/2, you sort of, that's like the one case where you don't have any quote-unquote bias, right? And so the chain is not leaning towards counting up or back down, right? When p is greater than 1/2, it sort of has a tendency to increment, right? And slowly, maybe it doesn't go all the way, doesn't go sequentially 1, 2, 3, 4, but over time, when p is greater than 1/2, you'll start kind of, hopefully you believe me, that there's going to be a tendency to move all the way around and complete the cycle and go around again, and so on. And so if you at least have a long enough movie, you'll be able to get a sense of whether this thing is reversible or not, right? And so for p greater than p basically not equal to 1/2, this really seems like an irreversible process, right? Not time reversible. But for p equals 1/2, that bias is not going to be there, and you just kind of don't know, right? It's going to be fluctuating, right? It's not clear where it's going to end up. And so, hopefully you can kind of follow this logic and maybe kind of have, can even sort of put it together on your own as well, hopefully. But let's see what I want to say. Yeah, I mean, I guess at this point, we sort of know roughly what we expect the answers to be, right? We expect the chain to be reversible for p equals 1/2 and irreversible otherwise. And now if we want to really establish anything, we want to try to get the stationary distribution, right? So there's a lot of ways to do this, and we kind of already have a guess that for general p this is not reversible, so local balance is not going to help us, potentially. Although if we were to establish local balance, then we'd prove reversibility, so we could try that for 1/2. Let me kind of suggest to you that my reason for picking this example is to say that you can use your intuition, right? Intuition counts for a lot with these problems. And so let me show you a sort of an overly difficult way to try to get the stationary distribution here. Surely it'll work, but it's just way too much work for what the actual answer would require. So, if I was kind of like, if I wasn't completely comfortable with, using intuition yet, then I would just, go with my global balance equations, right, and try to stick with those, and I'd start with a stationary measure, as I have here. And, I remember that I get one for free, so I put mu1 is equal to 1, and then I write down the global balance equation, which here would be, I write down the left-hand side, I pick the state 1, and then I have to ask myself, what states can I get to 1, 2 from? And that's states n and states 2. I go from state n with probability p, and I go from state 2 to state 1 with probability q, and so this is my global balance equation for state 1. So I get this one for free, and then I still don't get an answer. I kind of get a relationship between mu(n) and mu2, but not, nothing really final yet, so I write down the global balance equation for mu2, right? This one is just saying, how do I get to state 2? I can get there from state 1, or I can get there from state 3, right? I get there from state 1 with probability p, and I get there from state 3 with probability q, so this is my global balance equation for 2. And then you keep going, right? And then, you can try to solve these. Actually, it's more difficult than it would seem. Kind of a bit of a nightmare when you start writing it out, so I sort of stopped. And another approach is to try to look at this from a transition matrix point of view, right? So at least you could kind of code this up and solve numerical examples, right? So the finite state Markov chain, so you could write a computer program that maybe takes in the number of states, and it takes the value p, and then it assembles this matrix, right? This is going to be the transition matrix for this chain. Namely, from state 1, you can go to state 2 with probability p, right? And you can go to state n with probability q, namely 1 minus p, right? So that's this transition right there. And then so on, right? From state 2, you can go to 1 or to state 3, and then all the way to state n. State n can go to state 1 or state n minus 1. And I think I messed something up here. This is supposed to be a q here. Okay. So hopefully I've kind of been convincing enough that if you go with this approach, I'm sure you'll get the answer eventually. But sometimes it kind of pays to take a guess and use your intuition. And how do we think about the stationary distribution of the stationary measure? Well, what do we expect where do we expect this chain to be in after a really long time? I don't see kind of any preference for any particular state, right? There's what would be called in physics symmetry here, kind of everywhere. not symmetry maybe in the sense of transitions, but no one state is kind of distinguishable in some special way from the next. They're all interlinked together in the very same way. So, if you kind of ask me what's the probability of seeing state 3 after a long time versus seeing state 7 after a long time, I'd say I don't see why those should be different, right? And the 3 and the 7, there's nothing special about those, right? It's basically any two states. I don't see why the probability of any of the two states here, why there would be a difference. And so my guess for mu here would just be 1, or namely, when you solve for the actual probability distribution, you should get a 1 over n. And so sometimes, you certainly don't want to rest there, right? Just because you have a guess doesn't mean you're right. But we can certainly try to see if now these equations make sense, right, with our guess. If this is indeed the answer, and then it better satisfy all these equations. So if I do plug in a 1 everywhere here, does my left-hand side match the right-hand side? And it seems like that's actually going to be true. 1 is equal to p plus q always, right? That's every single equation there is going to read 1 is equal to p plus q, namely p plus 1 minus p, which is equal to 1. And so, and that's going to be true for all values of p. And this is kind of another one of those ways of getting at the stationary distribution, meaning guess it and try to verify global balance, right? Clearly, pi x is equal to 1 over n is a distribution over the n states. They're all non-negative and sum to 1, and they all satisfy global balance, right? As because the stationary measure just did. And so that was an easy one, right? So we just got the stationary distribution pretty much for free, whereas we would have had to work quite a bit, right? We're writing a whole program here, and here we're solving all these equations. It's way too much work, right? So sometimes it really does kind of pay to take a guess and just to calm down and think about sort of what do we really have here, and what do you expect it to happen after a long time, after a long run time of this chain. So now what of reversibility, and what of we kind of took a guess that for p not equal to 1/2, this is now going to be reversible, right? So we can kind of directly try, let's try local balance, right? Let's try to see if local balance holds for an arbitrary p. What would this mean? Well, it would mean, for example, that mu x times p, right? If we're in mu x and we transition with p to state mu x plus 1, right? The way we transition from x plus 1 to x is going to be q. This equation better hold, right? This is the version of local balance, whether you write pi there. I guess you could write pi or mu, it doesn't matter. Let me switch it to pi. So pi is equal to 1 over n in both cases. And so I get this basically saying that p over n, right, the n comes from the pi, so this is 1 over n, p over n must equal to q over n, right? This is the only way that local balance will hold, right? And so in general, clearly it's not true, with one exception, right? When p is equal to q, right, you have p equals 1/2, right? And that was exactly our guess, right? The unbiased random walk on a cycle is reversible because it satisfies local balance. Whereas when p does not equal to q, you have just a little tiny bit of bias, and either from the fact that local balance fails to hold for any pairs of state, not just one pair of state, for any pair of states it fails to hold. You see right away that this thing is irreversible, which is what we guessed, right? If you have a movie that you record this thing for long enough, you'll see eventually the bias creeping in, and this thing will move either one way or the other way, telling you or letting you detect which way time is moving. And I guess the only last thing to say is what of the time reverse chain? We also had a guess at that. The time reverse chain has the definition p prime xy is equal to pi y over pi x p y x, right? This was our time reverse chain, and here, right, everything is right. This is easy, right? This goes away, right? The pi's cancel. They're all these values are 1 over n. So here everything cancels, and so what do you get for the time reverse chain? P, so we can even be kind of specific. Pxy, let's say this one was transitioning from x minus 1 to x, right, in which case this was p, then the transition from x to x minus 1 would have to be p in the reversed process, right? So essentially, the fact that these two states are flipped, right, you're moving in two different directions. So when you put a p here, right, it's the flip one, the reverse direction would have to move with probability p. And when you put a q here, right, it's the reverse direction that has to move with probability q. So here, right, this is sort of the rigorous way to show exactly what was our guess, that the time reversed chain for this, the time reverse chain here is exactly the same diagram, but with p's and q's just flipped, right? And so, in other words, every p gets replaced with q, or otherwise, or just 1 minus p, and every 1 minus p gets replaced with a p, right? And so, and this is a rigorous way to say that, because this, this goes away, right? So yeah, so I guess the lesson here is that a lot, right, intuition can buy you a lot, right? You can kind of imagine this so to speak tricky problem like on a test or something, right, and then you're stuck, right, with this thing for half an hour. So always try to run this through with your intuition, and that will go a long way.